All right, so hello and welcome to this video. In this video, we're going to look at dimensionality reduction. And in particular, we're going to look at it kind of in the sense of the role that it can play in enabling predictive modeling. So one thing that is true of kind of the neural network architectures that have kind of risen to prominence in recent years for image classification, text classification, and so forth, that I think a lot of people maybe don't necessarily realize is that, a thing that really enables them to perform at the level that they do, at least in my opinion, is that they are extremely good at taking very complex high-dimensional data and coming up with a lower dimensional representation of that data that still captures a tremendous amount of the data's meaning and that variance. And ultimately, again, that is what has led to, again, some of the astounding performance of these models that we've seen. I mean, ultimately, they can take, again, very complex data and they'll come up with a lower dimensional embedding of that data. And that's essentially the raw material that those processes will use to either generate predictions, generate text and whatnot. So wanted to step back from neural networks for just a second. Let's just look at how far we could get with just flat out dimensionality reduction and some simpler machine learning algorithms for classification. So before we get into the code, I did want to show you. So I'm just going to go out to GitHub. And if you were to search for user:"Freeman Analytics, all right, I'm going to be putting the code that I go over in this video in this predictive modeling repository. So right now there's going to be two notebooks, this dimensionality reduction notebook. That's what I'm going to go through in this video. And then there's going to be a PyTorch introduction video that will follow. Both of those are currently in that GitHub repository, and we're going to be using the MNIST data, so got the data set up there as well. So if you want to find complete versions of these notebooks, they're going to be here. I'm going to be working through a partially completed notebook, so I'm not going to code everything from scratch. Basically working from versions of these notebooks with certain key cells left blank so that we can really step through those parts. All right, so I'm going to move over to a Jupyter notebook. So I'm running a Conda environment. I have scikit-learn installed. I have, of course, Jupyter Lab installed. Polars is installed. And then I also have a library called PacMap. So let me just show you that. So PacMap, this is going to be one of the dimensionality reduction techniques I look at. And you can just go out to this repository. I believe this is one of the authors of the paper describing the implementation. You can go in here and they do have a Conda package for that. So I'm using the Conda version installed from Conda Forge. All right, so I'm just going to open up this dimensionality reduction notebook. And just one thing on the file structure, and this is the same way that it's set up in GitHub. I do have a subfolder, so I'm working on this dimensionality reduction notebook. And it is in a folder where there is a subdirectory called data, and in that there are two Parquet files, that mnist_features.parquet and mnist_target_parquet. So that is the setup of the structure. All right, and what we're going to be doing, again, I want to kind of show you, again, just the kind of power of using, really good dimensionality reduction techniques for predictive modeling, because, again, I think, realizing this will help you kind of see the analogs to some of those, groundbreaking neural network architectures that we have today, because they're very good at dimensionality reduction. All right, and to do this, we are going to use the MNIST data. So all this code block is doing, the data is in two parts. So I've got the feature data in that mnist_features Parquet, and then I've got the target data in that mnist_target Parquet. So I'm just reading both of those data sets into separate Polars data frames. So our feature data and our target data. And for our target data, there was a column called class. I'm just renaming that to label and making sure that that is an integer. All right, so that gets read in. We'll look at this data shortly, but this is what we have. So in our feature data, we have 70,000 examples. So we have 70,000 rows. Each of those is going to correspond to a single handwritten digit, and it's going to have 784 features that describe that instance. Our target data is just going to have a single column. That's going to be the label for each of those 70,000 instances. Now let's talk just a little bit about this 784 features. So the MNIST data set, these are handwritten digits. These are essentially just black and white representations of handwritten digits. And each one of these values, these 784 columns or features that we have, that's going to correspond to a pixel value. So the images were 28 by 28 pixels. Okay, so that they were essentially square images representing these digits. And they're saved as 28 by 28. So if you do that multiplication, there's 784 unique values. And then so each one of the values in those columns is essentially going to be the pixel value for one of those 28 by 28 pixels. All right, so just to show you that, if I were to look at feature data and do the head of that, all right, so this is kind of what that looks like. This is what our feature data looks like. We've got a lot of zeros, which zeros would correspond to white on that grayscale spectrum. And then the values can go all the way up to 255, which would correspond to black. All right, it's kind of hard to look at this and see any meaning because, again, you know, the pixel values that we're looking at, that pixel 1, I believe, is that upper left corner. And then all the way out to 784, I believe that's that bottom right. So we're seeing predominantly areas where those pixel values would most likely be white because I believe those images are centered. So to help us visualize what this looks like, just wrote a little function right here. What it does, you give it an index, and what it's going to do is it's going to grab that row from our feature data, convert that to a NumPy array, and then reshape that so that it's 28 by 28. All right, this is going to plot that as a heat map. All right, so here's some of our pixel values. So in this case, I'm actually plotting out the label as well, so we know that, you know, what this is, because some of these are very poor examples of handwriting. So this is one example of a 5. Here's a 0, and we can look at a few of these examples and see that, okay, well, that's a 2, but this is our data set, right? All right, so that's a 5. That's a very interesting 5. Maybe we could even, as a human, mistake that as a 6. All right. So this is our data set, and the key thing to note here is that we have got a tremendous feature space. So if we look at our feature data, again, .head, right, we've got 784 columns. A lot of those values are 0 that are representing those. Now you can imagine if you were to just hand off this table of data to something like a decision tree classifier, maybe even random forest, any tree-based classifier, right? It's gonna either, you know, if we let the tree grow very large, it's going to be a very, very complex structure, and it's more than likely going to struggle to predict any type of meaning in this data, or give us a good predictive accuracy. And a big piece of this, right, is that, you know, if you think about how maybe a tree-based classifier would work, it's essentially looking at your feature space, in this case, our 784 pixel values, and it's saying, okay, well, if I were to split, if I were to essentially select this feature and figure out a point to make a split, what feature should I select and where should I make that split such that I essentially, you know, minimize the impurity of essentially the classes represented in each side of that split point, right? But if you think about it, if I'm looking at this 5 right here, and, you know, if I'm looking at, you know, pick any one of those pixel values, that's essentially, you know, would be, you know, one possible split point for a decision tree or a tree-based classifier. So any one of those individual pixel values. But in reality, for us, when we look at this to tell that this is a 5, or let's say that, you know, this is a 6, it's not necessarily the value of any individual pixel. It's the value of that pixel taken in consideration with the pixels around it. So essentially the context, right? And you can already hear, you know, when I'm talking about context, that is a term that's probably a lot more familiar to people now, at least in the context of machine learning, than it was years ago, right? Because we're talking about language models, and they need to understand the context of, you know, what we're talking about. And certain models might come out with an advertised context window. So context is very important. It's not, again, an individual pixel value or an individual piece of text or word. It's that word given the other words, or in this case, the pixel values that are around it. All right, so what we're going to do is we are going to use dimensionality reduction techniques to say, okay, well, we've got these 784 features. Can we come up with a lower dimensional representation of that features space that essentially allows us to capture, the majority of the variables, essentially learn that context and embed that into a lower dimensional space. Because if we can do that, then we can use that in a much more simple classifier to do predictive modeling. Okay. All right, so all I'm going to do is I'm going to break our data into a training and testing splits, which is very common practice. So in this case, I'm just going to use train test split from scikit-learn. So all of these things are imported up here at the top. So all of our imports are there. So we've got train test split. We may look at cosine similarity. We're going to use a random forest to do the classification. And there's that PacMap library. And I do believe this warning that I'm getting right here is actually from within PacMap. I think it's actually not a PacMap thing. I think it's a number warning. So hopefully they'll get that fixed in later versions. All right, so we're going to do our test train split. I'm essentially just stratifying on our targets. And then, so let's just take a real quick peek at what these data sets look like. So I'm just saying, okay, we'll keep 10% of our instances in the test set. So if I were to look at xtrain.shape, right, so we've got 63,000 of our instances pulled into that training data. And again, we've got 784 features. If we were to look at xtest, right, 7,000. And then, of course, ytrain and ytest would correspond in shape, or at least the number of rows, to the training and testing feature sets. All right, so again, just xtrain, that's my feature data for my training set. Ytrain is my labels for my training set. Xtest is my feature data for my testing set. And ytest are the labels for my testing data. All right, so the first technique that we're going to use to do dimensionality reduction is a very common, very well-established technique. It's been around for a long time, has a very strong mathematical foundation. And again, it can be useful in a lot of different contexts, right? And that's going to be principal components analysis. And again, before we start going into this, remember, we're not focused on dimensionality reduction. That's not the goal of this. We're not going to do a survey because there's a lot of dimensionality reduction techniques. My key point, or my goal and objective of doing this video, is to kind of show you how, if we can get really good at doing dimensionality reduction, in particular nonlinear dimensionality reduction, it will enable us to do very impressive things from a predictive modeling standpoint, which is kind of a key concept that's embedded into these state-of-the-art models we're seeing today. All right, so principal components analysis is a technique for dimensionality reduction that is based on identifying principal components of maximum variation in a data set. So in our case, we've got our feature data, and it's going to say, okay, well, can I identify, kind of these principal components of maximum variance in that data? And the assumption is that, okay, well, the components with those highest variance, those are going to be the most important components. So if I can figure out what are those directions of highest variance, well, then that's going to be the thing that really allows me to learn something about this data. Another assumption that it makes is that relationships between your features are linear and that your data is centered around the mean. All right, and because of this last one, we're going to do a little bit of scaling of our data set before we hand this off to PCA. But it's going to be, pretty straightforward to do using scikit-learn. So PCA is built into scikit-learn. And again, one thing I really want to emphasize here is that assumption of linearity among features. So it makes that assumption. Of course, if you want to learn more about the mathematical intuition and the modeling and how it identifies those core principal components, feel free to look it up. I mean, there's a tremendous amount of literature and references out there regarding PCA, because again, it's a very mature approach. All right, so let's go ahead and do this implementation. I'm going to be looking over at my cheat sheet. All right, so scikit-learn has a module called decomposition, and they have a PCA class there. And then we're also, to essentially handle this data is centered around the mean assumption, we're going to do some scaling of our data. We're just going to use a standard scaler. And in scikit-learn pre-processing, we want to import standard scaler. All right, we're going to define or instantiate an instance of that standard scaler class. And we are going to fit that on our training data. So again, we're going to fit it on the training data, and we will apply that to our testing data, but we're assuming we've only seen the training data. All right, so that's going to be our fitted scalar. And then what we're going to do is I'm going to use PCA. I'm going to make an object, a variable called PCA. And what I'm going to do is I'm going to define a PCA, a principal components dimensionality reduction method with two components. So in components is going to be equal to 2. All right. And what we're going to do is we are going to fit that on our transformed X-train data. All right, so this is how that would work. And then at the very end, so this should, just to show you, there's going to be an explained variance ratio. Let's take a look, make sure that's running. Fantastic. So in this case, we're running PCA on a scaled version. And this standard scaler, just so that you all know, I mean, it basically standardizes features by removing the mean and scaling to unit variance. So it's almost like a standard normal distribution type of scaling. And that's, again, kind of what they're assuming right here, data centered around the mean. So we're assuming it's essentially normally distributed around the mean values. All right, and here's our explained variance. So we've got two components that we fit, and this is going to be the variance captured or explained by that first component and then the second component. Now, of course, if we fit many components, right, in this case, I've increased that to 10, we can explain more variance. Each one of those components, you know, explains some variance. And the way that PCA works is that first component that it returns is going to be the one that explains the most variance, right? Because it essentially assumes that that is the most important. So we can always explain more variance by including more features. And if we want to see the total variance explained, right? So if we do 10 features, we can explain 27%, right? If we do 100 features, right, we can explain 70%. If we do 2 features though, which again, this is an extreme case of dimensionality reduction, right? We're only going to explain 9%. And this is where I'm going to leave it because I'm really wanting just to show, again, the power of a very strong dimensionality reduction technique. So, of course, we could expand the number of components we allow for PCA, but in this case, we're just going to use 2. It is easier to visualize so we can see exactly what's going on, but we can think of this is an extreme dimensionality reduction application. We go from 784 to 2. And even with that, you know, we're able to explain nearly 10% of that variance. So, I mean, you know, going from 784 to 2 and explaining 10%, that's actually a pretty good, you know, amount of variance that we can explain. All right, so we fit this model. So now we have a PCA model. So if I give it some scaled data, right, it knows how to interpret that and do that dimensionality reduction. So what we're going to do is we're going to create essentially a training and a testing data set that's based on those PCA embeddings. So instead of our actual feature data, it's just going to be the dimension reduced version of that using this PCA method. All right. So what I'm going to do is for each one, I've got this PCA model that's fit now for 2 components, right? We just did that fitting here. And if I do a transform, all right, so we can call transform on a scikit-learn object once we fit it, because it's essentially learned how it's going to do the reduction. I'm just saying apply this reduction that you learned to a different set of data. And I'm going to give it, again, that scaled X train. I'm going to copy that and give it that scaled X test as well. All right, so this is going to be our PCA EMB for embedding. That's going to be for our training set. And then this will be for our testing set. All right, so if I were to look at either one of these, let's just get our testing set and I'll get maybe the first 10 rows, right? So this is our 2-dimensional representation. So based on our testing data, right? So for the first row of our testing data, well, in the actual testing data set, that corresponds to 784 feature values, but we've reduced that dimensionality to only 2, and hopefully we've maintained some variance that's meaningful so that we can learn something. All right, well, let's visualize this. So I'm going to use polars to do this. So let's go ahead and I'm going to create this PCA embedding data frame. I'm going to say that that's going to be a polars data frame. I'm going to pass it my training set for now. And I'm going to define a schema so that I get 2 columns. So I'm going to say first column's D1, D2, so that's just dimension 1, dimension 2. And then I'm going to add a column. So I'm going to say with columns. And I'm going to do a series. Whoops. The name of that series is going to be label. And the values are going to be, so Y train, let's just take a look at that right now. So Y train, that's currently a polars data frame, right? So what I'm going to do is I'm going to say Y train dot get column, that label column, and then I'm going to convert that to a NumPy array. Let's see, where's my error? So I've got to close off my series. There we go. Great, so we've got our 2 PCA dimensions and their corresponding labels. And so now I'm going to use matplotlib. Let's say 1, 1. Let's do 6 and 5. And I'm just going to be a little bit lazy and convert this straight from a pandas data frame. So I'm just going to say, okay, well, polars to pandas, and then we'll call it dot plot. We'll say the kind of plot will be a scatter plot. Our X is going to be D1. Our Y will equal D2. We're going to say the color is equal to the value in the label column. Let's say, we don't have to worry about alpha. Let's just do a CMAP equals, I believe it's tab 10. We'll put that on our axis. And then just because I'm picky, I'm going to take off those right, and top spines. So we'll do a set visible false. And then we'll do a plt.show. Fantastic, right? So this is what our essentially PCA model learned, right? So this is our data, at least in this case, our training data, mapped into this lower dimensional space, right? So we can see as dimension 1 is varying, and dimension 2 is varying, and then we've got our colors indicating our labels. Now, if you look at, kind of that region between, D1 values of 10 and 30, the majority of those are mapping to that blue, which would correspond to 0. So it seems like the model has learned, it's kind of grouped those zeros together. And if you look, there's some other regions like the orange, maybe the gray, that there is some separation, the orange being the 1 and the gray being the 7. And they're kind of on that left side when your D1 values are between -10 and 10. And it seems like D2 is really what differentiates. But right there in the middle, right, it's like there's a lot of a mixture of points, right? And moreover, everything kind of got lumped together in this one big glob, even though we do see that it can kind of separate out the zeros maybe fairly well, the zeros and the 7s. I mean, they're still kind of all in this one big continuous glob. So not a lot of really good separation. And because of this, if you think about it, if we're trying to train a classifier with this data, we can imagine it's going to struggle, right? It's going to have some challenges in doing that. So let's see. All right, so what we're going to do is we are going to come up with, we're going to use a random forest model. We're going to do a multi-class random forest to see if we can learn to take that reduced dimensional vectors and correctly predict those labels. All right, so what I'm going to do is I'm going to define a random forest classifier. We'll just do in estimators equal to 100. I'm going to say max depth equals 10, maybe. Should be fine. I'm just kind of putting those numbers in there. We might play around with it just a minute and see if we could get it better. That might be a little, because we only have 2 dimensions, but I'm hoping it can use those 2 dimensions to kind of maybe parse up this space. So if it uses that max depth, we can allow different split points that maybe use the same dimension. That'll really kind of help it hone in on certain areas. Maybe we need to reduce that, though. We'll try in a second. I'm going to say mjobs just equal to 6 for right now. Let it use a few cores. And then I'm going to do clf.fit. And I am going to fit that on my PCA embedding train. And the y's, I'm just going to take y train. And then I'm going to say 2 numpy. And let's just look at what this is doing. So I'm going to pull that little, so y train 2 numpy gives me that vector. And I'm just going to use ravel to make that a one-dimensional array. So I'm just getting my labels down as a one-dimensional array. Fantastic. All right, so that's going to go through and fit our classifier. And I'm going to bring in just a little bit more code to compute the accuracy. So I'm going to say our training accuracy is going to be, I'm going to use our fitted classifier to predict, all right, based off of our that training. So it's going to make a prediction of what's the correct label. And then I'm just going to compare that to the values in y train, of course, represented as a one-dimensional vector, to see if those things are the same. So if I were to run that right now, it should fit. And right now, this train accuracy, it's just a bunch of trues and falses. So I can sum those up. So if I were to pop a sum at the end, all right, so that's how many essentially trues. So how many times the prediction match the values in y train. And if I divide that by the length of, say, that PCA embedding, that's going to convert that to a predictive accuracy. All right, so I'm just going to move all of that right there. Great, so that's going to give me my training accuracy. And then let's go ahead and do this for our test. All right, so that needs to convert over to test. And then we'll do y test here. And then this right here will also be test. And then I'm just going to print those accuracies out. Print. And I'm just going to say train accuracy equals, and let's just do that to 3 decimals and do it as a percentage. All right. See if that runs. It does. And these values might be a little bit different than what we're seeing in the one that's posted online. It could just be, again, it's due to probably different random values being done in this random forest classifier because I'm not setting a seed, but it's pretty close. I believe the values that I had in the notebooks posted on GitHub are like 42.046 and 37.757. Overall, very, very close. What I am going to do is I'm just going to go ahead, since we've done a little bit of coding outside of the cells, I'm just going to go ahead and do a good restart clear outputs and just run back down to that cell. Fantastic. All right. Let's see. Very good. There's our predictions. Great. All right. So up to this point, what we've done, we've taken our data, we've used PCA, which again assumes linearity between features. And then it also is saying, hey, if I can find directions or principal components, which represent directions of maximum variance, those are most important. It identifies those. We use PCA to fit a model with 2 components, and then we handed those off to a random forest classifier to see if it could figure out how to best use those values for those 2 components to predict the correct class label. And even though I used a max depth of 10, let's just see if I were to reduce that to 5. Yeah, we actually lose a little bit on the train, not too much on the test. So it actually is doing a little bit better, and it's not necessarily overfitting too much. We are getting a little bit of a discrepancy right here. So maybe the best value is somewhere maybe 7, something like that. But overall, we tend to be in this ballpark of around 37% accuracy on our test set. All right, so let's see where it misses. So this was code that was already in this notebook. I'm just going to hand those predictions and that model generate those predictions. We're going to look on our test set now. So this just generates a data frame with our actual values, actual labels from the test set, and our predicted values from our classifier. And what we're going to do is we're going to look at the proportion of time that it correctly classifies digits. So this is the proportion of instances that are correctly classified by instance using those PCA dimensions. Right, so you can see like the 0 and the 1 and even the 7 and the 2 maybe, those tend to be, the highest. And if we were to go back and look at our visualization, right, we talked about in that essentially that lower right hand area of that blob, those are the zeros. It seems to have kind of figured out, hey, I need to move those over in this reduced dimension space. So it seems to have separated those fairly well. And similarly, we made, a similar note about the ones, which are kind of in that, that region between maybe -10 and 0 on the D1 scale and -10 and 0 on the D2 scale. And then the sevens as well, but everything else was kind of mixed. All right, and this is kind of what we see in these prediction results. Now, this dashed black line, what is that representing? Well, we have 10 different digits, 0 through 9, and if I were to just ask you to randomly guess or make a guess about the class or a label for a particular instance, you'd essentially have a 1 in 10 chance of getting that correctly. So this is kind of like your baseline accuracy. I mean, you can see in the PCA model, we do better than that random baseline in most cases. We actually don't do better than it in all cases, right? So the 3 we tend to struggle in, but we learned something, right? I mean, it's better than random. It did fairly well for ones in particular, right? I mean, that's almost 90%, it seems like. But overall, it's not amazing, right? We would not want to deploy this in production because we're going to have a lot of mistakes. And let's just see what some of those mistakes are. So this is a heat map where on the vertical axis, that is the actual value for an instance. And then on the horizontal axis, that is what we predicted it to be. So if you're looking at, okay, that upper left cell, that's where the actual value is 0 and we predicted it's 0. So we did that correctly 68.8% of the time. If we look, when it's actually a 1 and we predict it's a 1, we do that about 90% of the time. So that was the case that we saw it perform the best. But overall, right, it's kind of, we make a lot of mistakes, a lot of interesting mistakes. If we kind of look along the diagonal and see, which ones did it do the worst for, well, clearly it's a 3. A lot of times it seems to have misclassified a 3 as a 2 or a 6 or even a 9. So a lot of confusion there. All right, so in this case, right, we see that we learned something, right? But we talked about, we definitely don't want to deploy this in practice. There's going to be a lot of errors. So even though the dimensionality reduction technique did allow us to go from 784 to 2 and learn, some degree of information, right? We had the predictive accuracy. We do better than baseline in a lot of cases. Is still going to be very error prone, right? I wouldn't want to be making mission critical decisions relying on the predictions coming out of this method. All right, so what if we could come up with a better way of reducing dimensionality, right? And again, the reason I'm going down this direction is because, to me, some of these new neural network architectures, they're extremely good at this. They take very complex, very high dimensional data where context matters, like in our case with images, and they're able to come up with really good reduced dimensional embeddings of these that we can use for various tasks like classification or sentence similarity. So that's really what they've learned to do. So I'm going to look now at another dimensionality reduction technique called PACMAP, which is essentially a shorthand abbreviation for pairwise controlled manifold approximation. All right, so again, I've got the link to the GitHub repository right here. This is a recently developed method. I think it's by a group of statisticians out of Duke. I could be wrong, but I do believe that is true. Very nice. And one thing that it does, so PCA is kind of looking globally at all of your data and it's saying, well, I'm trying to find these dimensions in the overall data of maximum variance. And it's kind of trying to figure out globally how are things moving. And again, there's a lot of good, mathematical intuition that's built into it. but it has to make some assumptions, right? That linearity. So PackMap does not require the assumption of linearity, and instead of worried about global, it actually considers both a local scale, right? So making sure that, okay, within a certain neighborhood of points that are close to one another, have I got those distances or that variation between them captured accurately? And then it also does a global phase as well. But instead of, just focusing on that global phase, again, it's based off of, pairwise comparisons within a certain neighborhood of points to make sure that it gets the local and the global piece. It's a really nice algorithm. I believe there's a talk on YouTube from one of the co-authors on the paper. It's really interesting to hear them talk through that. So I encourage you to look at that, at least from my perspective. It is a phenomenal technique. A lot of people will say that, it's primarily, it's developed for, visualization. It can't be used to reduce dimensions or clustering. Again, I understand, some of the sentiment from kind of the dimensionality reduction purists there and the people that are looking at techniques. And I'm not saying this is the best technique out there, but I have used it for clustering purposes or, to come up with those reduced dimensionality embeddings in a lot of practical cases, and it has proven to perform very well for that. So I don't believe, it's an only for visualization type of technique, whereas maybe something like a TS&E, I would think is more aligned with that. But at least in my experience using this in practice, it fares out pretty well for the purpose of reducing dimensionality and allowing clustering of high dimensional data sets. So let's see that in practice. All right. So let's take a look then. So it's going to be a very similar kind of workflow. The one thing is, it makes no assumption about linearity, and we actually do not need to scale the data in this case. It probably would be useful if your features are, widely different scales. So maybe you're looking at housing prices in one column, or you're looking at a housing data set in one column's price versus the other one's number of bedrooms. I mean, it might be helpful, right, to get things in the right scale. But in this case, we don't necessarily, all the features are mapping to values between 0 and 255. And the model makes no explicit assumption that things are going to be centered around 0. So we're just going to feed the data to it raw. And the way that we would do this is we'll make a reducer object, and I'm going to look in PackMap. All right, I am going to use a random state here. It will warn me that I'm using a random state. And one thing that's a little bit different, so I'm going to get my training embeddings. So I'm going to say PCA embedding train. We're going to do PCA here. We're doing PackMap EMB train, and that's going to be our reducer. And what we're going to do, previously we had done like a fit first and then a transform using that fitted object using scikit-learn. The way that we will do this, and this may change, of course, this library is fairly new, we're going to call fit transform just on our XTrain model. Okay. And then when we're doing this fit transform, we can actually do we've got the reducer defined. When we call fit transform, it's going to fit that reducer and go ahead and do the transformation on our XTrain. Then when we make the call on our testing data, we don't have to do the fit anymore because we've already done the fit as part of that method. But what we do have to do is we have to tell it a basis, right? So it needs to know the data that was used to do that fitting process, because again, it's based off of, the looking at neighborhoods or looking at points that are close to other points. All right, so we give it the data we want it to transform. And then we also have to provide, so that's going to be an X argument. And then we need to give it a thing called a basis. So this is basically, okay, well, when you did the fit, what was the data set that you used to do the fit on? All right, it's going to take a second. All right, so it's warning me that I've set a random state, which is fine. That's exactly what I intended to do. All right, while we're waiting on that to run, I'm going to go ahead and copy up some code. So I'm going to go up here to our PCA where we did this visualization. I'm going to go ahead and copy what we did to create that Polars data frame. All right, I'm going to bring that down. It's actually going to be exactly the same. So that's still running. Again, it's a little bit more computationally intensive, but I'm going to say this is going to be our pack map. It's finished. All right, so I just finished up. So I'm going to do our pack map embedding df, and to do that, I'm going to give it our training embeddings. That's still going to be fine. And then here I need to change to my pack map embeddings. All right, so let's see how pack map did. And here we see that the dimensionality reduction technique, the visualization of this is much different, right? So remember, this is what we got when we applied PCA. All right, so kind of this one big glob. We did see that it was able to kind of push certain digits to the boundaries of that blob, but overall, kind of indistinguishable. Versus when we look at PackMap now, we see really, really nice distinguished clusters, right? I mean, of course, there is some mixing. It's not perfect, but overall, we do see some kind of nice globs, and they make sense, right? So if we think about this orange glob that's kind of between D2 values of 0 to negative 1.5 and D1 from 5 to 20, right? That corresponds to your ones, and that seems to be very well separated. If you look at that upper blob, right, that's kind of between D1 values of negative 5 all the way to 10, and then D2 values of 5 to 15, well, we actually see three different classes represented, but there's still good separation there. So what are the three classes? Well, it looks like it's the 9, the 7, and the 4. So these are all digits that would have kind of that hook over the upper right. Right, so it seemed to have learned some structure fairly well. And we can imagine that if we're going to use a tree-based classifier on this data and use it to kind of parse up this space, it should do a lot better because we tend to see a lot more clear separation between the various classes. So just based on the visual, we can immediately look at this and say, well, gosh, yeah, it's going to be much easier to classify this. We could even probably sit here and come up with our own rules to make a simple like decision tree structure that would be fairly accurate for this data. All right. So let's do that. I'm going to go back up here, copy my scikit-learn code. So we're going to do our classifier. I'm going to copy all of that down. So previously we got about 41% accuracy on the train set and 37% accuracy on the test set with PCA. Let's go down and run that for PackMap. All right, so we've got our classifier. I need to change that from our PCA embeddings to our PackMap embeddings. All right. Let's see, did we fit yeah, we've got our PackMap embeddings train. That's good. So PackMap embeddings train. All right, that needs to change. And then this one needs to change to test. And then in our divisions, right, we need to make sure that I'm just going to go ahead and update. It should be the same length, but to make that look correct, right? All right, let's look at the accuracy. All right, so in this case, right, so we get 97% accuracy on our training set and 95.571% accuracy on our testing set. So, we're wrong. We make the incorrect classification in less than 5% of instances. Whereas before, remember on that test set, we were only correct 37% of the time. Right, so in this case, again, all we're doing is dimensionality reduction. This is kind of the key thing I want you to understand. Technically, what we're solving here is a vision problem. And, the way that if I were to ask you, okay, well, you've got these different methodologies to solve this, and, we've got digits and we're trying to classify them, we would immediately think of this as an image classification problem, right, which would typically require a convolutional neural network. Right. Instead of doing that, all we're doing is we're saying, well, you know what, we got a really large feature space. Can we come up with a really, really good way to bring that down to a lower space and maintain important information while we do that? Right. So we're going from 784 to 2. Right. So let's just think about, the degree of that, because that's very impressive. Right. So we're going to have 2 features from 784. Right. So we've got, less than 1%. We're retaining less than 1% of the number of features, right? It's a tremendous amount of dimensionality reduction. And of course, if we gave it additional features, maybe we did PackMap with 3 components or 4 components, we could probably get more information and do even better. But going all the way from 784 to 2, we get a predictive model that is 95% accurate, which to me is astounding, right? And it shows very, very clearly how powerful it can be to be able to come up with high quality, low dimensional representations, which to me, again, is kind of like a core idea that is behind the success of a lot of these neural network architectures, in particular the transformer architecture, that it has just demonstrated astounding performance on a variety of tasks lately. All right, so let's see just where it makes its misclassification. So I'm creating that data set to just look at the actual versus predicted. As you would imagine, with this high accuracy, a lot of times we get the correct classifications for most classes. It looks like if it were, I was going to say it was struggling, maybe with a 3, a 4, and an 8. So I would imagine it's misclassifying some 3s and 8s. And then if we look at those misclassifications, we can confirm that. So if we look across that row, again, that vertical axis is indicating what the label actually was. And then the horizontal is what we predict. So if we look across that row for the 3s, right, we can say, well, it is, the 3, it tends to misclassify a 3 as either a 2, a 5, or an 8. So it gets a little bit confused there. So those are some of the dimensions that it really struggles with. All right, so that is it. Hopefully, this was pretty understandable. Again, the goal was not to go through the mathematics of dimension or PCA or PackMap, but more or less to kind of motivate this idea of if we can come up with a way of taking very high dimensional data, bringing that down to low dimensions, retain variability, we can use that for some, a variety of tasks, and we can achieve really, really amazing performance. This is not a neural network, right? This is just dimensionality reduction. Another huge benefit of this that we're not even talking about is, if you think about it, originally we got 784 dimensions. Well, certain problems can be much larger, right? So think about text, right? These text models, they're considering contexts of thousands of words at a time. Kind of storing that information. Can we take words or a body of text and represent it instead of maybe storing those individual words or integers representing those words? Can we come up with a lower dimensional representation? Because 2 things, if we can, first off, storing that representation, storing that information is going to be a lot less expensive. Well, for example, in this task, what if we had hundreds of millions of digit representations? Well, if we store the original embedding, which has got 784 features, it's going to take a huge amount of space, right? If we're storing those as floating points. But if we store that as a 2-dimensional representation, I mean, we've scaled back our infrastructure needs, our data storage needs, orders of magnitude, right? So that's tremendous. So from a storage perspective, it can be very important. And also from a computation, because doing computations on 784 dimensional vectors is going to be more computationally expensive than doing that with 2-dimensional. So there's a lot of benefits all the way around if we can do this well, right? All right, so that is going to conclude this video. Again, the completed notebook is up on GitHub.